Welcome back to Agent in a Nutshell. Today, we are breaking down the architecture of the Agent Payments Protocol, specifically AP2 version 0.2. This node graph represents standard legacy payment rails, which are built on a single, uncompromising assumption: a human being is sitting at the keyboard. When an authorization request hits the network via ISO 8583 standards, it expects that a person has actively authenticated on a trusted surface to approve the charge. But the moment an autonomous AI agent steps in to execute a purchase on behalf of a user, that structural assumption collapses. Legacy risk engines are trained to spot anomalous velocity and non-human interaction patterns. When an agent discovers a product, assembles a cart, and attempts to check out at machine speed without human biometrics, the network automatically flags it as fraud and kills the transaction. This creates an immediate operational failure for merchants and issuers. Without a human explicitly clicking buy, there is no clear way to prove the agent actually authorized the agent's specific cart, making liability in the event of a dispute impossible to assign. To process agent-driven commerce at scale, the ecosystem requires a translation layer. We need a way to provide deterministic cryptographic proof of user intent to systems that were only ever designed to handle probabilistic human behavior. This is the exact engineering problem AP2 version 0.2 was built to solve. AP2 functions as a specialized authorization layer rather than a payment rail. It never holds funds, moves fiat, or processes cryptocurrency directly. This architectural diagram shows its role as an open-source extension, layered specifically on top of interagent communication networks like A2A, the Model Context Protocol, and the Universal Commerce Protocol. Its sole function is to generate verifiable digital credentials, or VDCs. These credentials translate the complex natural language intent of an AI agent into a standardized cryptographic format that legacy banking systems can ingest and understand. For merchants, these credentials create a mathematically sound, non-repudiable audit trail. They have cryptographically signed proof that the agent was authorized to execute that specific transaction. For networks and issuers, the credentials deliver explicit metadata. Instead of guessing if a transaction is fraudulent, the bank receives a clear signal detailing the exact presence and modality of the agent. The result is dispute-grade evidence. Merchants can secure agent-driven checkouts without having to tear out and replace their core processing logic. This topology map outlines the strict 5-role architecture required to generate this cryptographic evidence. The sequence starts with the human user and the designated shopping agent acting on their behalf. The remaining 3 infrastructure nodes consist of the credential provider managing the payment token, the merchant endpoint fulfilling the order, and the merchant payment processor routing the transaction. This schema shows how these 5 roles communicate by exchanging a specific state machine of contracts called mandates. Under the hood, these mandates are formatted as selective disclosure JSON web tokens. The integrity of these tokens is enforced by hardware-backed ECDSA P256 signatures. The most critical token in this flow is the checkout mandate. This artifact explicitly locks down the negotiated details of the purchase, indexing the exact SKUs, constraints, and the total price. Once the cart is finalized, a cryptographic hash representing its exact state is mathematically chained directly into the mandate's payload. This chain guarantees that the exact cart constructed by the agent is the exact cart authorized by the payment network, creating a mathematical barrier against token replay or amount manipulation. To actually move funds against that locked cart, the system requires a secondary credential known as a payment mandate, which authorizes a specific financial instrument. How this mandate gets signed depends on the execution mode. In a human-present modality, the user is brought synchronously into the loop to review the finalized cart and explicitly sign the mandate themselves. But autonomous commerce requires a different approach. A user can sign an open mandate ahead of time. This establishes strict, pre-approved constraints, like maximum budget limits or specific allowed merchants, before any shopping begins. This enables the human-not-present modality. The agent can monitor the market, negotiate a cart, and autonomously sign the closed mandate hours or days later, bounded entirely by those pre-approved constraints. The payment mandate then acts as a metadata courier. It passes the specific modality signal, flagging whether the human was present or not, directly through the authorization packet to the issuer. By receiving these explicit modality signals, legacy issuers can dynamically adjust their risk scoring models, safely greenlighting autonomous purchases based on cryptographic proof rather than relying on standard behavioral heuristics. However, the presence of strong cryptography does not render the entire system secure by default. Cryptography protects the execution state, but it cannot protect the reasoning process of the agent itself. Recent empirical red teaming research, notably the Whispers of Wealth paper, highlights a critical vulnerability in how these agents operate prior to the mandate generation. AP2-equipped shopping agents remain susceptible to indirect prompt injection. Attackers can execute a branded whisper attack, embedding hidden adversarial prompts into product listings. When ingested, this manipulates the agent's logic, skewing cart construction toward the attacker's items before the variables silently alter. This manipulation succeeds because it occurs entirely upstream. The agent's decision-making is compromised before the cart is finalized and long before the ECDSA signing process begins. AP2 guarantees that the cart wasn't tampered with in transit. It provides zero guarantee that the AI made a logically sound purchasing decision in the first place. Despite these architectural caveats, the immediate deployment of AP2 version 0.2 is structured for rapid adoption by relying almost entirely on existing tokenized card networks. The protocol is engineered so that mandate artifacts embed quietly into standard ISO 8583 messaging and API authorization payloads. Because the data travels along established rails, major processors like PayPal and networks like MasterCard can ingest agent presence context natively, without requiring a parallel settlement network. Looking at this standards documentation, we can see how Google solidified this integration by donating the AP2 specification to the FIDO Alliance, establishing an open governance structure supported by major ecosystem players. This adoption strategy clears the largest hurdle for enterprise rollout. It allows the payment industry to verify autonomous transactions immediately, avoiding the impossible task of ripping out decades-old global infrastructure. This timeline illustrates the near-future roadmap, which pushes the protocol beyond traditional tokenized fiat. The newly introduced X402 extension expands AP2 to handle real-time bank transfers and Web3 stablecoin routing, opening up direct agent-to-agent financial settlement. Over the next 5 years, AP2 mandates will evolve from optional metadata into a mandatory policy enforcement layer, blocking any autonomous traffic at the API gateway that lacks a valid cryptographic signature. AP2 provides the mechanism to force the inherently probabilistic output of large language models into a state of deterministic execution. Standard, verifiable cryptography remains the only viable bridge between the fluid logic of autonomous agents and the strict zero-tolerance demands of legacy financial risk engines. Thanks for watching, and we'll see you in the next one.